Whew. Okay, thank you all. It's very exciting to give the first talk of the day. Especially appreciate everyone who got their ICLR papers out yesterday and still came. I hope you're at least a little bit awake. I want to talk today about some research we've been doing mostly at UW before I joined Facebook part-time, but that we're also sort of slowly bringing into the infrastructure here. And the idea is that we want to do a relatively rich semantic analysis of a sentence and try to get some notion of its meaning, and I'll be more precise as I go. But that also we want to think about, how would you get lots and lots of data for doing this? Or how would you do it in different domains? Or it won't be in this talk, but someday, how would we do it in other languages and other settings like that? And just to highlight that Luhang, Nicholas, and Julian deserve all the credit, and the majority of the talk will be on a paper that appeared at ACL this year, which was an honorable mention paper. So I'm going to focus specifically on semantic role labeling. And so the idea here is that we want to find verbs in a sentence, and we want to figure out what is that sentence claiming. So within that sentence, who did what to whom, when, and where. And this is often formulated as a type of graph labeling problem. So we would call the verb the predicate. We want to draw edges between the predicate and the arguments. And those edges often have some sort of label on them, like this is the agent of the activity, or this is the patient of the activity, this is the time it happened, and so forth. Now, from the perspective of this talk, there's going to be many different formulations for how to label the edges. I'm going to introduce another one as I go along, but the key idea is that this overall graph structure gives you a good idea of sort of the core backbone of the semantics. And that maybe the edges, although they are important, the graph itself is also equally important, and that's something we'll pay attention to as we go and think about how to get those graph structures correct. Now, something you might be thinking with the recent trends in NLP is, why are we going to have these intermediate latent structures? Why are we going to do this semantics? Let's just go end to end. Let's just optimize for some end task. I'm sympathetic to that worldview, but I don't think that story's been totally, that decision hasn't been totally made. So for the purpose of this talk, I'm just kind of assume that these structures are good to build. They have been used in lots of applications. Even if they're not currently being used now, I think we should be investigating how to bring them back. And we can talk more in the question session and so forth about that if you're interested. Okay, so I'm not so good at humor, but I'll make a few attempts. I want to convince you that SRL is a challenging problem and that even people struggle, at least in some extreme cases. So, if I say Hershey bars protest, it probably doesn't have to do with this little cute guy here. Probably something else is going on. In the second case, there probably isn't a little zombie that's refusing to do something after they've died. And in the third case, we're probably not literally talking about a violin case, okay? And these are actual structural ambiguities in the semantics. So if you were to look at the SRL annotations, you would see that bars is actually a verb, and you have to hook up the arguments this way. I've left off the labels. I'm just focusing on the structure here. Miners refuse to work is sort of after some horrible event happened, and so forth and so on with different structures. In terms of actual accuracies on this task, SRL is pretty challenging. So it was originally introduced in 2005, at least one particular formulation called PropBank. There's a lot of great progress over the next 10 years on various aspects of the task, but the core sort of in-domain test number sort of didn't move much. And one reason for that is that there's just like a lot of this really interesting linguistic phenomenon that you should care about if you want to claim you're understanding language. They're absolutely crucial for doing this task. So I'm just going to very quickly go through some of those phenomena just so we understand it. So the same semantic relationship can appear in lots of different syntactic configurations. So it could be a verb with different mapping onto the syntactic arguments, or it could be a noun. One hallmark of these semantic relationships is that they can be quite long. So for example, a verb, the actual agent of the verb can appear quite far apart in the sentence. And then, if you've done any work on syntax or NLP more generally, there's this notion of all these sort of canonical hard cases like coordination and PP attachment and so forth, and those all show up here too. So, with the pizza, probably your friends aren't literally in the pizza when you're eating it, okay? All right, so I got at least one chuckle. All right. And then finally, we're all should really care about sort of out-of-domain things. So, a lot of data for these sorts of things were annotated, in the 90s. There was newspaper text, and then you take these same models, you go run them on some other text, and as we all know, if you've been doing NLP things, they just completely fall to pieces, okay? And so a big part of the talk today is going to be addressing that and saying, how would we fix that? Well, maybe we just need to label a little data in that new domain. Well, how do we do that? That's really hard, and actually, if we change the formulation a little bit, maybe we can do that. Maybe we can train better models and so forth. And then quickly just do a few slides on sort of, before we do our new SRL formalism, what's the kind of current best model for the classic formalism of PropBank? We also was from my group at UW this year. Just to give you a little flavor of modeling them, I'm gonna mostly talk about data, new data formulation, and then I'll come back and do some modeling on that new data, talk a little bit about future work. So the key challenge is that we're gonna need to build these edges, these sort of structures between verbs and their arguments. And the way the sort of currently state-of-the-art approach works is, you use your normal contextualization, BILSTM, so forth, to get embeddings for all the words. And then the idea is that you actually construct span embeddings. So you enumerate all of the n-squared spans in a sentence. I won't tell you how, but there's a pretty straightforward function for getting embedding for each. And then you run a classifier on all pairs of spans, okay? And it says, for these pairs of spans, do they appear in a predicate-argument relationship with each other? And if so, what label should they have, okay? And you run this model all the way through, and basically you have a state-of-the-art SRL system. The nice thing about this approach, this is building on work over the last few years, say 2 years or so, is that there's no NLP pipeline, there's no part-of-speech tagger, there's no parser, you're just sort of doing this end-to-end deep learning directly from the available data. And if you look at performance numbers, one amazing thing is sort of after 10 years of basically no progress on the task, very little progress, we've now gotten sort of a 40% error reduction by kind of throwing away the NLP pipeline and doing these end-to-end methods. Okay? And one cool thing about this, so you can see the older pipeline methods, the first deep learning methods, and then our most recent method, which also includes Elmo. You can see some stars for ensembles and so forth, so there's a lot of moving parts here. But from my perspective, the cool things are that we've got this really big error reduction, and that the blue is in domain, the green is an out of domain test, that it actually, you're still lagging out of domain, but we're not really overfitting. The models actually are working and they are generalizing out of domain, whereas some of the first deep learning models kind of dipped there and eventually everything came back. Okay? All right. So now you're experts on how these models work with those 2 slides. And the cool thing, this sort of is a freeing perspective for me, this idea that you can just sort of throw away the pipeline, train directly from these semantic labels. And we thought, okay, now how do we go and get like a whole ton of these semantic labels, right? No longer do you have to know how to do part-of-speech tagging or parsing or anything. You just need some sort of semantic supervision. You train your models directly from that. Will that free us up to start thinking about new languages, new domains, and so forth? We're not quite there yet, but we've taken some first steps, and I want to tell you where we are along that trajectory. The classic way that this data is annotated is you have sort of an ontology of frames. So each verb has a bunch of senses, and when you see a new verb, you've got to think, does it fit in one of the existing senses? If so, what labels are available for it? Which labels should I put on which arguments? And how do I scale the whole thing up? So I sort of have this iterative process of going through all the verbs, looking at all the sentences where they appear, and in the end, you have sort of a 100-page annotation manual, this big ontology of verbs, and it becomes sort of very difficult to maintain and update over time, although you get some really beautiful structural and ontological information out of it for sure. And what we said is, well, look, okay, there's not going to be any free lunch here, so we're going to have to give up on something. So we're going to actually throw away the ontology and focus more on the structural information. And what we're going to do is figure out a way of doing a proxy task of question answering, where you can get that overall graph structure of the semantics in a very scalable way. So in the end, by the end, we'll be able to get sort of 70,000 sentences labeled in a week on Mechanical Turk. It'll be high quality. It'll give you much of the information you had before, and you'll be able to train really good, deep end-to-end methods from it. Okay? That's where we're going. Now, the idea here is that this task has to be so simple that I can teach you to give me annotations in 2 minutes, okay, or 1 minute. And so to show you that, I'll just do it right now. So the sentence is, my landlord increased the rent this year. In the QA-SRL annotation scheme, I'm going to show you a verb, and you're the annotator. I'll ask you to write questions that use that verb, whose answers are other phrases in the same sentence. Okay, so you're already seeing the first question here. Who increased something? What's the answer? My landlord. What other questions could you ask? You could say, what was increased? When is something increased this year, and so forth, okay? It turns out, we sort of started all this research about 2 years ago, and in the first effort, which I'll talk about in a second, we spent a lot of time sort of relating this to existing structures, and the second effort, which will be the bulk of the talk, we sort of figured out how to sort of scale it up and get a lot more annotation from it. But the rough takeaway is that, this works very generally for lots of different verbs. It's not perfect, it's a little bit noisy, but you can get really rich structures about how all different kinds of arguments and relationships between arguments and adjuncts and verbs and so forth, okay? And, but the real challenge here, we're asking annotators to write questions and answers. The real hard part is recall. So here is a sentence with 4 verbs, and you can quickly sort of scan through and get a little bit more feel for the task. So Alan Turing published an article in which he proposed that machines could be tested for intelligence using questions and answers, right? So this is actually the Turing test, not QA-SRL, but it's a little cute analogy there. Now, the tricky thing is when you ask an annotator to sit down and write all the question-answer pairs for a sentence, what we found through iteration is that they're good, they give you nice high-precision results, but it's hard to get them all. So generally, every question-answer pair you get will be very good, but you won't get them all, and you have to work on that. So our first solution in the initial work, just to kind of show that this was valid, was to say, okay, what we want to do is just have trusted annotators. So we're just going to train them a little bit and give them some feedback. It won't be as scalable, but let's just figure out will the overall scheme work. And that was the paper that Luheng did in 2015. And we further constrained things a little bit. So we said, okay, look, the questions can come from a templated class. So that's why you're seeing these someones and some things showing up. So to specify a question, you just have these 7 little drop-down boxes. It was actually in a spreadsheet. And you go about this, and you sort of enumerate as many of these as you can. And you get high-quality stuff because you can actually pay them hourly and train them. All right. So if we compare this to existing formalisms like PropBank, the key change now is that the semantic edges, instead of having something like an arg0, arg1, or agent patient on them, they actually have natural language questions annotating the relationship between the verb and the argument. So we've given up something. We don't have this beautiful ontology, but in the other way, we can be much more open and scalable and so forth. We did some work comparing to PropBank, which is the most commonly used. These are just some agreement numbers. I wouldn't worry about them too much other than to say that we have reasonable agreement on overall and on the core roles, but the adjuncts, which are these sort of wheres and what and hows and so forth, are actually a little bit trickier. And we'll see some examples of that later in the talk. It's not perfect, but you get a lot of really good information. And for those that are more experts in the audience that know the PropBank annotation scheme, here's a confusion matrix of the WH words in our questions with the PropBank roles. And you see roughly what you would expect. Something like a where question is going to the location role, but it's actually quite messy and interesting. And language is hard, and the words blur across the ontological boundaries. Okay. So now we said, okay, this works. It's pretty clean. You can build good things from it. How do we scale it up? So how do we build a much better parser? How do we get much more data, build a better parser, and also deal with these issues of recall in a maybe a little bit more algorithmic way? So the key idea here was that, okay, we can just do a mechanical Turk pipeline. We can be a little bit more careful about it. And this is Nicholas and Julian's paper at ACL this year. And so the idea is, okay, you do the same thing. You ask the Turkers to write questions. You have another round of Turkers that will go and actually verify that those questions get the right answers when you show it to them. And you just have to be a little bit careful about the interface. So we get a careful mechanical Turk interface. We sort of have auto-suggest and sort of pricing incentives so that they really want to suggest more. But in some sense, this is just engineering and not really research. And we're more excited about the research it will enable by getting them more data. The results here were, once you get this debugged and deployed, is that we could do 75,000 sentences, 300,000 edges. Cost about 33 cents a verb, took 9 days, and we did completely open text. So this is all available on the website, which I'll show you at the end, and you can go and download and play with it. And now the really nice thing is that, the sort of 2 slides I showed you earlier on models, turns out those port directly over to this data. With sort of minor modifications, we're able to train very similar models on this data and get nice parsers. And again, you'll be able to go play with a demo after the talk online. Okay, so let me talk to you a little bit about how the modeling works. Here are just two little pictures from previous SRL papers. So the top one is that graph structure that I was talking about where you predict the edges between the spans. Of course, people have also done SRL as BIO tagging. So for each verb, you could do begin, I, and O of each of the arguments. The key challenge now in adapting these models to the QA-SRL setting is just these edge labels, right? So instead of having this relatively small set of discrete edge labels, we have this, it's still discrete because we have templates, but quite large set of possible questions that you can put on each edge. But the key idea and the sort of relatively simple thing that you can do is say, look, we're just going to break this into two steps. So we'll take that old model. This is the same diagram I sped through in the first part of the talk. And we'll first just use it to do unlabeled edge detection. So we'll predict what the arguments should be without actually giving them a label. You could do that in the span-based or the BIO manner. And then we'll have a second step where, given the embeddings that come with whatever sort of unlabeled detection you've done, you can just basically treat it like a seek-to-seek problem and decode the question that would go on that edge as a multi-step process over the slots that are involved. Okay? And those models work quite well, and I'll take you through maybe sort of 5 or 6 slides now that quickly show you how that works and show you some results. Here are some results. So just for step 1 in the argument detection, this is the unlabeled detection, either exact match or a lenient metric that looks at overlap. It turns out you can do quite well in argument detection. Question generation is a little bit harder. You've got to set all these slots. You can do it one of 2 different ways. You can independently predict each slot, or you can have sort of a sequential model that will sort of do a little bit more like a language model and go through them in turn. So the sequential model, what we're going to do is just reuse that embedding out of the model for that particular span if we think it's an argument, and just independently predict each one. And then the only real slight twist that comes with the sequential model, people should be pretty familiar with these models now, is that because it's a template, we don't actually have to reuse the parameters for each slot. So we have separate parameters for each one. That works a little bit better. Okay. So then you run this model, and you can either say, did I get the entire exact question correct, or did I get the individual slots correct? And it's actually quite difficult to get the exact match, although I'll show you later there's issues of paraphrase here. So one issue with this task is that this, multiple questions can be associated correctly with each age due to paraphrase. And so, that's something I'll come back and talk to you a little bit later in a human eval. And then the end-to-end numbers look like this, where you have to correctly get the span and get the question. This is, very strict, getting everything perfectly correct. And I'll do a human eval again that will show in a second that you can do much better in practice. Okay. So just very quickly now, the idea is we have this sort of interpretable thing. We can quickly get people to annotate it. But then you can actually do even more. So because it's easy to understand this task, you can show people the questions. You can have them answer it. But you can also tune the model. So that'll give you a human eval. But you can also tune the model and say, OK, let's turn up our recall. Let's propose more and more questions. And then let's only have the Turkers answer them and not propose them. Right? So proposing questions is quite hard. It has these recall issues, but answering them is quite easy. So you basically just turn up your recall dial. You go out, you just validate it. It's going to be much cheaper, and you can fill in the gaps in your data and retrain your models. Okay, so we did an experiment like this. The takeaway story is that we were able to add about 50,000 new questions to the original 300. They're all very high quality. Cost went down by about a half. There's a little bit of bias because of the model here, but we did show that if you throw that extra data in and retrain, the model gets better along all the different metrics. And we can look at these precision recall curves. Here, the recall is the number of questions asked, because we don't really have a good notion of the goal max number of questions, but this is the number of questions asked. And this is a human eval, so now we're not having issues with paraphrase. We're actually showing them all the questions and asking if they're correct. If you control for sort of roughly the same number of questions per verb as in the training, our model in a human eval is getting about 82% accuracy. So it's actually working quite well. This is for question generation, and this is for arguments, where here the numbers are maybe even slightly lower than before, but we're actually doing quite well. Okay, so here's my last slide, just a little bit of a qualitative evaluation. So we did quite well here. In particular, the model picks up lots of interesting extra cues. So if you're under sort of a modal or some sort of negation, you actually have to negate the question before you can ask it, and the model will automatically pick that up and do it correctly. There's some issues with boundaries. You may not get the boundaries perfect, but you do a good job of getting the right thing. And then every now and again, you'll get something sort of totally wrong, where, especially with these auxiliaries and so forth, they're hard to attach and they're hard to get right. Okay? All right. So that's the end. We have this scalable approach. We're training models. We want to go even further. We want to go beyond verbs and do all the words in the sentence. In theory, this should apply to different languages. This should be able to be useful for domain adaptation. And in general, there's this philosophy of tasks that you can teach people to give you labels for in 5 minutes or less. Okay, and that philosophy I'm very excited about. And the question is, could we do that for all of NLP? What would it look like for other tasks? How do we get this similar thing going? For the QA-SRL in particular, I encourage you to go to QA-SRL.org and have a look. There's some very slick demos that Julian and others have come up with. We're not professional designers, but they're fun to play with. And the data and code is all there, and you can download and use it. I'm happy to maybe take one question or something if I can. Yeah, so the question is, what if the Turkers don't understand the domain text? So that's a really great question. Thanks, Mifeng. So, for example, if you're doing biomedical or some specialized domain. Yeah, and the answer there is it's true there's no sort of free lunch. Often from syntactic cues alone, you can get good labels. So we've had some experiments where non-bio people can actually do reasonable in bio text, but it's gonna ramp up the noise for sure. So maybe get multiple annotators. Or, I guess the other answer is, it's still better. So previously you would have required a linguist that also knew the medical text. And now we only require someone that knows the medical text. So, it's a step in the right direction, but I don't think we have the best story there. We haven't really solved, that aspect of it quite yet. All right. Okay, one more question?
Yeah, this seems similar to work in natural language inference, where you're kind of asking the annotators to generate sentences to create kind of unique labels for the task. And what they found in that task was that if you use representations trained on that task, they tend to transfer well to other tasks. Did you explore that at all, whether the representations learned from the things that you learned in your annotations transfer to different tasks?
Yeah, that's a great question. So basically in other tasks lately where we've been able to get a lot of data, we've been able to train models and they'll transfer well. So, pre-training on NLI gives you cool sentence encoders, for example. No, but I have worked a lot on sentence encoding lately, and this is definitely something we want to try soon. We have that mindset, but we've just recently gotten the data to start looking at it. And I think it would be very exciting. I can't promise it will help, but we would really love for it to. And it would help with some of these end task complaints that we sometimes get. Okay, I should stop. I'm probably over time. Thank you.